Orientable surfaces. A surface S is called an orientable surface if there is a function n such that for each point x, y, z in S, n of x, y, z is a unit normal vector to S at x, y, z, and n varies continuously over S. The vector function n is called an orientation of S. If S is an orientable surface, then there are two possible orientations of S. Indeed, if n is an orientation of S, so is negative n. A classical example of a non-orientable surface is the Mobius strip. You could form a Mobius strip by starting with a long strip, giving it a half twist, and then connecting it end to end. The Mobius strip is non-orientable because it really only has one side. You could get from any position on the Mobius strip to any other position by just walking straight across it. If a surface is orientable, as we've said, there are two orientations. Here's a picture illustrating a typical surface with the two orientations of the surface. For this particular surface, you can see there's an upward orientation and a downward orientation. The normal vectors in the second picture to the right are the negatives of the normal vectors in the first picture to the left. Suppose a surface S has equation z equals g of xy, or equivalently, z minus g of xy equals 0. If we let capital G of xyz equals z minus little g of xy, then the gradient of capital G is the vector with components negative partial of g with respect to x, negative partial g with respect to y, 1, and then the length of that gradient is therefore the square root of the square of partial g with respect to x plus the square of partial g with respect to y plus 1. So in this case, an orientation is given by the gradient of g over the length of the gradient of g, which is the negative partial g with respect to xi minus partial g with respect to yj plus k, over the square root of the partial g with respect to x plus the square of the partial g with respect to y plus 1. This is called the upward orientation of the surface because the k component is positive. If we negate this vector, we get the second orientation, which is the negative of this one, and that would be the downward orientation of the surface because in this case, the k component is negative. Alternatively, suppose an orientable surface S is given in parametric form by a vector function r of uv. If the cross product of the partial derivatives is never 0, then an orientation of S is given by the cross product of the partials divided by the length of that cross product. If the surface S is the boundary of a solid region G, then we say that S is a closed surface. The positive orientation of a closed surface S is the one where the normal vectors point outward from G. The negative orientation would be the one where the normal vectors point inward from G. So here's a picture of a sphere as an example showing a positive orientation. Notice the normal vectors are pointing outward. And if we take the negatives of those, we get the negative orientation where the normal vectors are pointing inward. Let's try an example. Find the positive orientation of a sphere of radius a when the sphere is parametrized using spherical coordinates. Go ahead and pause the video, try this example yourself, and resume the video to check your answer with mine. We start by parametrizing the sphere using spherical coordinates. R of phi theta equals a sine phi cosine theta I plus a sine phi sine theta j plus a cosine phi k, where phi goes from 0 to pi and theta goes from 0 to 2 pi. We take the cross product of the partial derivatives. We've done this computation many times before, and we see that we get a squared sine squared phi cosine theta I plus a squared sine squared phi sine theta j plus a squared cosine phi sine phi k. We then take the length of this cross product. Again, we've done this many times, so I will just mention that the final answer is a squared sine phi. It follows that an orientation is the normal vector function little n, which is the cross product of the partials divided by its length, and we're left with sine phi cosine theta I plus sine phi sine theta j plus cosine phi k, which is 1 over a times r of phi theta. In other words, it's 1 over a times the original vector valued function. This is the positive orientation, because it's pointing in the same direction as the radius vector and therefore outward from the sphere. Flux. Let F be a continuous vector field defined on an orientable surface S with orientation n. The surface integral of F over S, also known as the flux of F across S, is the surface integral F dot ds, which is defined to be the surface integral of F dot little n ds. Note that if capital N is the gradient of G, or capital N is the cross product of the partial of R respect to U and partial of R respect to V, then we have the following. So just recopying the definition of the flux, we have that the flux of F across S is the surface integral of F dot n ds. Now, little n is equal to capital N over the length of capital N. And when we change from the surface integral to the double integral over R, we throw in an extra factor of the length of capital N. After this simple cancellation, we get the double integral over R, F dot capital N dA. So notice that when we're actually computing a surface integral of F over S, or equivalently a flux integral, we don't actually need to find the orientation. We only need to find capital N by either computing the gradient or the cross product of the partials, depending if we're doing it as a non-parametric or parametric surface. And we can just take the dot product of the vector field with capital N and go right to the double integral over the region, skipping over several of these steps. Let's try an example. Find the flux of the vector field f of xyz equals zi plus yj plus xk across the unit sphere x squared plus y squared plus z squared equals 1. For your convenience, I put the formula for computing a flux integral on the above right there. The important part is the part in red, which allows you to do the flux integral in the quickest way possible. Go ahead and pause the video, try this example, and then resume the video to check your answer with mine. Okay, we start by parametrizing the sphere using spherical coordinates. R of phi theta equals sine phi cosine theta I plus sine phi sine theta j plus cosine phi k. Phi goes between 0 and pi, and theta between 0 and 2 pi. We take the cross product of the partials. Again, we've done this computation many times. So the answer is sine squared phi cosine theta I plus sine squared phi sine theta j plus cosine phi sine phi k. So note that I don't need to normalize this vector because we're going to be using capital N, which is what this is equal to. We could just go right ahead and take the dot product of this with the vector field F. So we get z times sine squared phi cosine theta plus y times sine squared phi sine theta plus x times cosine phi sine phi. Now, technically, before we put this into the integral, we should probably change z, y, and x into what they are in terms of phi and theta, but we'll do that in just a moment. The limit, since we're doing this d phi d theta, the theta limits are 0 and 2 pi, and the phi limits are 0 and pi. Let's go ahead and replace z, y, and x by what they are in terms of phi and theta. Z is equal to cosine phi, so we get cosine phi times sine squared phi cosine theta, or equivalently sine squared phi cosine theta. Y is equal to sine phi sine theta, so we get sine cubed phi sine squared theta, and x is equal to sine phi cosine theta, so we get cosine phi sine squared phi cosine theta. Combining the first and third terms, we then get 2 sine squared phi cosine theta plus sine cubed phi sine squared theta. I just copied the middle term down. And the final answer here is 4 pi over 3. The double integral is straightforward, so I will leave it to you to check the details. Let's try another example. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Evaluate the flux integral f dot n ds, where f of xyz equals x to the 4th I plus 2y squared j plus zk, and s is the part of the ellipsoid 1/4 x squared plus 1/9 y squared plus z squared equals 1, with z greater than or equal to 0, and n is the upward orientation of s. Okay, we start by parametrizing the ellipsoid. r of phi theta equals 2 sine phi cosine theta I plus 3 sine phi sine theta j plus cosine phi k, where phi goes from 0 to pi over 2 and theta goes from 0 to 2 pi. Let's just pause for a moment to see how I got this. We could start by just parametrizing the unit sphere, and that would be sine phi cosine theta I plus sine phi sine theta j plus cosine phi k, and then stretching the sphere in the x direction by 2, because the square root of 4 is 2, and in the y direction by 3, because the square root of 9 is 3. So that's one way to get this parametrization very quickly. Now, also note that since we're only looking at the part of the ellipsoid where z is greater than or equal to 0, phi is only going from 0 to pi over 2. Remember that phi equals 0 is the positive z-axis, and phi equals pi over 2 is the xy plane. Now let's just quickly check that the parametrization that we just defined actually satisfies the equation of the ellipsoid. So 1/4 x squared plus 1/9 y squared plus z squared, substituting in 2 sine phi cosine theta for x, 3 sine phi sine theta for y, and cosine phi for z, we get 1/4 4 sine squared phi cosine squared theta plus 1/9 9 sine squared phi sine squared theta plus cosine squared phi, which is sine squared phi cosine squared theta plus sine squared phi sine squared theta plus cosine squared phi. Now we can factor out sine squared phi from the first two terms, giving us cosine squared theta plus sine squared theta, which is 1. So we just get sine squared phi plus cosine squared phi, which is equal to 1 by the usual Pythagorean identity. Okay, now we need to take the cross product of the partials. This is a very similar computation to ones we've done already. You might want to pause the video and just check that this computation is correct. We get 3 sine squared phi cosine theta I plus 2 sine squared phi sine theta j plus 6 cosine phi sine phi k. We now take the dot product of the vector field f with this cross product, and we get x to the 4th times 3 sine squared phi cosine theta plus 2y squared times 2 sine squared phi sine theta plus z times 6 cosine phi sine phi. Now, replacing x, y, and z by what they are in terms of phi and theta, we get 48 sine to the 6th phi cosine squared theta plus 162 sine to the 4th phi sine cubed theta plus 6 cosine squared phi sine phi. The limits on the integrals, well, the theta limits are going from 0 to 2 pi, and the phi limits are going from 0 to pi over 2. That comes right from the parametrization. The answer to this is 4 pi. The integral itself is straightforward, so you should go ahead and check carefully that you get the same answer as me. One more example. Evaluate the flux integral f dot ds, where f of xyz equals yi plus xj plus zk, and s is the boundary of the solid G enclosed by the paraboloid x squared plus y squared plus z equals 1 and the xy plane. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. So here's a picture of the situation. Here is the solid G. Notice that the solid G actually consists of two surfaces. So S is actually S1 plus S2, where S1 is the paraboloid and S2 is the disk in the XY plane. Notice that the normal vector to the disk is just pointing straight down. Let's go ahead and do S1 first. So if h of xyz equals x squared plus y squared plus z minus 1, then we could get a normal vector n by taking the gradient of h, and we get 2xi plus 2yj plus k. So the surface integral over S1 f dot ds is the double integral over r f dot n dA. And when we take the dot product of the vector field f with n, we get y times 2x or 2xy plus x times 2y or 2xy plus z times 1 or z. And when we add that up, we get 4xy plus z. And now we have to replace z by what it is in terms of x and y. Well, z is 1 minus x squared minus y squared. So we'll go ahead and do this in polar coordinates. So we replace x by r cosine theta and y by r sine theta. So we get 4r squared cosine theta sine theta plus 1 minus r squared. And remember, since we're changing to polar, we multiply by an extra factor of r, dr d theta. Now, theta is going from 0 to 2 pi, and r is going from 0 to 1 because we're integrating over the region that is a disk of radius 1. Okay, so distributing that r gives us 4r cubed cosine theta sine theta plus r minus r cubed. And when we integrate with respect to r, we get r to the 4th cosine theta sine theta plus r squared over 2 minus r to the 4th over 4. Plugging in the 0 and 1, we're left with cosine theta sine theta plus 1/2 minus 1/4. Then integrating with respect to theta, we know that the cosine theta sine theta is just going to come out to 0 because we're going from 0 to 2 pi. And 1/2 minus 1/4 is 1/4. So we get 1/4 theta from 0 to 2 pi, or 1/4 times 2 pi, which is pi over 2. And now we still have to do the flux integral over S2. So that's equal to f dot negative k, because an orientation for S2 is just negative k. So that comes out to z times -1, which is negative z. And since z is equal to 0, we could just replace that by 0 and we get 0. So the second surface doesn't contribute anything new to our answer, and the final answer is pi over 2.